Welcome to our 5-part video series on Introduction to Quantum Computing for Beginners. In this series, we aim to provide a comprehensive overview of the basics of quantum computing, starting from the ground up. Whether you're a student, a professional, or just someone curious about the topic, this series is designed to make quantum computing accessible and easy to understand. From understanding the basic principles of quantum mechanics to exploring the latest developments in quantum algorithms and quantum computers, we'll be covering everything you need to know to get started with quantum computing. So sit back, relax, and let's dive into the fascinating world of quantum computing together. Part 1. Introduction to Quantum Computing and Definition and Explanation of Quantum Computing. Quantum computing. Quantum computing is a field of computing that uses the principles of quantum mechanics to process and store information. Quantum computing is a new and rapidly evolving field in computer science that leverages the principles of quantum mechanics to perform computational tasks. Unlike classical computing, which relies on bits that can only exist in two states, 0 or 1, quantum computing uses quantum bits, or qubits, that can exist in multiple states simultaneously. This unique property allows quantum computers to perform certain computations much faster and more efficiently than classical computers. Quantum computing has the potential to solve problems that are impossible for classical computers to solve within a reasonable amount of time. For example, quantum computers can be used to crack encryption codes, simulate complex chemical reactions, and optimize large-scale logistics problems. In addition, quantum computing has the potential to significantly advance fields such as machine learning, cryptography, and financial modeling. Despite its potential, quantum computing is still in its early stages of development, and there are many technical and scientific challenges that need to be addressed before it can reach its full potential. Qubits. Quantum computing uses qubits, which are quantum mechanical systems that can represent both 0 and 1 simultaneously, as the basic units of information. This property, known as superposition, is what makes quantum computing so powerful. Unlike classical bits, which can only exist in two states, 0 or 1, qubits can represent both 0 and 1 at the same time. This allows quantum computers to perform many calculations in parallel, which can greatly speed up certain types of computations. The second key property of qubits is entanglement. The second key property of qubits is entanglement, which allows them to be correlated with each other in ways that cannot be described by classical physics. This correlation enables quantum computers to perform certain operations much faster than classical computers. For example, quantum computers can perform a database search in a time proportional to the square root of the number of items in the database, whereas classical computers require a time proportional to the number of items in the database. This exponential speedup is what makes quantum computers so promising for certain types of problems. However, the implementation of qubits is challenging due to their delicate nature and the need for extremely low temperatures to preserve their quantum properties. Quantum algorithms. Quantum computing solves problems by using quantum algorithms that take advantage of the unique properties of qubits, such as superposition and entanglement, specially designed to take advantage of the unique properties of qubits and perform tasks that are not possible with classical computers. These algorithms are based on the principles of quantum mechanics and are specifically tailored to the strengths of quantum computing. Some of the most well-known quantum algorithms include Shor's algorithm for factoring large integers, Grover's algorithm for unstructured database search, and the quantum simulation algorithm. Quantum algorithms are designed to perform certain tasks much faster and more efficiently than classical algorithms. For example, Shor's algorithm can factor large integers exponentially faster than the best-known classical algorithms, while Grover's algorithm can search an unsorted database in a time proportional to the square root of the number of items, which is exponentially faster than classical algorithms. Speedup. Quantum computing has the potential to provide exponential speedup for certain computational tasks compared to classical computing. These speedups have led to a great deal of excitement about the potential of quantum computing to revolutionize fields such as cryptography, finance, and chemistry. However, there are still many technical challenges that need to be addressed before quantum algorithms can be implemented at scale, and research is ongoing in the development of more efficient and robust quantum algorithms. Applications. Potential applications of quantum computing include cryptography, drug discovery, financial modeling, machine learning, and optimization. The development of practical, large-scale quantum computers is challenging due to the difficulties in controlling and maintaining the quantum state of qubits and implementing quantum error correction. Difference between classical and quantum computing. One. Representation of data. Classical computing uses bits, zeros and ones, while quantum computing uses qubits, can represent both 0 and 1 simultaneously. In classical computing, information is represented using bits, which can only exist in two states, 0 or 1. This binary representation of data allows classical computers to perform operations such as arithmetic, logic, and memory storage. However, this binary representation can be limiting when dealing with complex problems that require a large amount of information to be processed and stored. Quantum computing, on the other hand, uses qubits to represent information. Unlike bits, qubits can exist in multiple states simultaneously, allowing them to represent both 0 and 1 at the same time. This property, known as superposition, enables quantum computers to process and store information in a much more efficient and flexible manner. Additionally, the correlation between qubits, known as entanglement, allows quantum computers to perform certain operations much faster than classical computers. These properties make quantum computing a promising technology for solving complex problems in fields such as cryptography, finance, and chemistry. 2. Parallel processing of data. Quantum computing allows for parallel processing of multiple computations at once, while classical computing processes one calculation at a time. 3. Problem-solving approach. Classical computing follows deterministic methods, while quantum computing uses probabilistic methods. 4. Speed of computation. Quantum computing has the potential to solve certain problems much faster than classical computing. 5. Limitations. Classical computing is limited by classical physics, while quantum computing is limited by the laws of quantum mechanics. Historical background of quantum computing. Richard Feynman. Richard Feynman was a theoretical physicist who made significant contributions to the fields of quantum mechanics and particle physics. He was also a gifted teacher and science communicator, known for his ability to explain complex scientific concepts in simple terms. The early concept of using quantum mechanics for computation was first proposed by Richard Feynman in the 1980s. Other pioneers are David Deutsch, a physicist at the University of Oxford, and Peter Shor, a mathematician at AT&T Bell Labs, developed key algorithms for quantum computing. A quantum algorithm was first experimentally realized in 1998 by a team of IBM research scientists. 6. Progress. Over the past 2 decades, significant progress has been made in the development of quantum hardware and software, leading to the creation of functional quantum computers. For example, several companies, including Google, IBM, Honeywell, and Intel, have developed quantum architectures using a variety of hardware and software platforms. 7. Commercialization. Companies such as IBM, Google, Microsoft, and Alibaba are investing heavily in quantum computing research and development, with the aim of bringing quantum computing to practical applications. Explanation and quick review of quantum bits, qubits. Definition. A qubit is the basic unit of information in quantum computing, similar to a classical bit in classical computing. Representation. Unlike classical bits, which can only be either 0 or 1, qubits can exist in a superposition of both 0 and 1 simultaneously. Coherence. Qubits must be kept in a state of coherence, meaning they must remain in a delicate quantum state, to perform quantum computations effectively. Entanglement. Qubits can also become entangled, meaning the state of one qubit is directly linked to the state of another, allowing for faster quantum processing. 8. Limitations. Building quantum qubits is a complex task that faces several technical challenges. One of the biggest challenges is quantum decoherence, which refers to errors that arise due to environmental factors such as temperature, electromagnetic interference, and material defects. Another challenge is scalability, which involves creating a large number of qubits that can be controlled and operated reliably. Additionally, precise control and measurement of individual qubits is a difficult task, requiring sophisticated techniques. The materials used to create qubits must also be compatible with the demands of the qubit system, including requirements for low noise, high stability, and scalability. Finally, integrating qubits with classical control and communication electronics is a challenging task that requires new technologies and architectures. Despite these challenges, significant progress is being made in the field, and researchers are actively working towards practical quantum computers. Thank you for watching part 1 of 5 of Introduction to Quantum Computing for Beginners. In the next video, we'll explore quantum algorithms and applications.